Hi, in this video we will discuss the invertibility condition for square matrices in terms of their rows and columns and new notions that we have introduced, something like linearly independent or spanning and so on. And at the end we will have an extended version of the fundamental theorem of invertible matrices. Let's start with the version of this theorem which we have so far. It's about a square matrix. Any square matrix, and it gives us 5 different ways to check if a matrix is invertible. Out of all the ones that we would use today are these 3 in terms of linear systems and in terms of the row echelon form. Before I start, I like to have this remark that when you have a square matrix, or any matrix actually, and you multiply to a column vector, then if I denote the columns of this matrix by C1, C2 up to Cn, and the vector itself is x1 up to xn, then the matrix multiplication, what it gives us is x1, c1, the linear combinations of the columns with the coefficients coming from the components of that vector x. So this is an observation, very important, and it's easy to see. If you have that in mind, now we can go ahead and start finding new statements here. I will start working on 2. What does it say? It says that for every b in Rn, Ax equal to b has a unique solution. Well, it means that it has one solution, and one solution means what? Means that these numbers are there, so it means that every vector b in Rn is a linear combination of columns of A. Very nice. So every vector can be written as linear combination of A. Fancy word for that was what? Was that columns of A span the whole Rn. Yes? So it spans the whole Rn. And, well, this means what? This means that column space of A, which is Rn, we already know, is n-dimensional. So dimension is n-dimensional subspace. As a result of that, if subspace is n-dimensional, every basis of column space of A has n vectors. Very nice. But we have specifically one way to find a basis for column space. Remember, we row reduce matrix, and then we find the columns from the matrix A corresponding to columns in the row echelon form which has leading one. So since we are going to have n vectors in the spaces, it means that reduced row echelon form of A has n leading 1. Well, the only reduced row echelon form, n by n reduced row echelon form with n leading 1 is the identity matrix. So reduced row echelon form of A is the identity, n by n identity matrix. And this is the condition for This guy is 4, and we know that it is equivalent to condition 2. Since this statement goes around, it means that all these statements here are equivalent. In particular, columns of A spanning the Rn is equivalent to second condition, or I can say that I can now write A is invertible if and only if columns of A, the columns of A span the whole Rn. This is a new statement. We didn't have this statement in our fundamental theorem of invertible matrices. This is now new one, and we can use it. Well, another version that will be useful is where we start the third condition. Look at this. Ax equal to 0 has only the trivial solution. So the third one. But Ax is linear combination of columns. What does it say? It says that the only way to write the zero vector as a linear combinations of the columns of A is the trivial version, the trivial way. It means that we need to put all the coefficients equal to 0. But this, when you have a set of vectors and the only way you can produce 0 as linear combinations of these guys is when you put all the coefficients equal to 0, this has a name for us. This is definition for those vectors, in this case columns of A, are linearly independent. And well, that is a new version. A is invertible. Not only columns of A span the whole Rn, but also A is invertible if and only if columns of A are linearly independent vectors. That's the second version. But if you put these two versions together, means that, well, if I start A is invertible, then on one hand, I know that this is equivalent with the columns of A span Rn. On the other hand, it is equivalent to saying that columns of A are linearly independent. If a set of vectors have these two properties, we have a name for that. Columns of A form a basis. This is the definition for basis. Yes, they're linearly independent and they span the subspace for Rn. Well, that's a nice version. Let me write it separately also. A is invertible if and only if the columns of A form a basis for Rn. Well, if columns of A span Rn, so that means what? So columns of let me just write it here, columns of Rn span the whole Rn. This means what? This means that, well, this is a different way of writing that. The column space of A span, the column space, I don't need to write. The column space of A, which is the span of the columns, is equal to Rn. And well, Rn is n-dimensional, so dimension of the column space of A is n. Well, we have a name for dimension of column of a space. That is a rank of A. That's a different version here. A is invertible. I'm writing all of them as equivalent to A being invertible. But as you can see, I'm always getting something a little bit different at the original version. And the proofs you're seeing here is a little bit different than the proofs you will find in your book. Okay. I will, yes, then let me close this box also. Now, an interesting version of this guy will be, we know that by the rank theorem, we know that rank of A, this is in general, plus nullity of the matrix A, these add up to the number of columns, in this case n. So if we have n a rank of A equal to n, well, plugging in that equation, n plus nullity equals to n, then that means that nullity of A is equal to n minus n, which is 0. And this is two-sided thing. And well, that will give me another version. A is invertible if and only if nullity of A is equal to 0. Rank must be n, but nullity needs to be equal to 0. This is nice. Now, well, so far all the things we have discussed was about the columns. How about the rows? Well, all these things can be related by one easy fact, that rows of A are columns of A transpose. So if A is invertible, then we know that rank of A is n, but rank of n and this is equivalent. Rank of A and rank of A transpose are same thing, because rank of A transpose, this is equal to dimension of a column space of A transpose. This is same thing as dimension of row space of A. That is just rank of A. So rank of A and rank of A transpose are the same thing. So this means that rank of A transpose is equal to n. Well, then write down all the conditions that we have. So columns of A transpose need to be linearly independent, but columns of A transpose are rows of A are linearly independent. or columns of A transpose span Rn, but columns of A transpose are the same thing as rows of A span Rn, and this is equivalent to rows of A form a basis. So exactly the same thing happens for rows and columns. Form a basis for Rn. So all these three versions I will put in one big box. These are also new versions or new statements that we will add to our new version of fundamental theorem of invertible matrices. Okay, let's all put all these guys together in one big version of fundamental theorem. Your book writes this version as the version 2. It has all the 5 versions that we had before. Now we added rank of A needs to be equal to 0. Nullity must be 0. Also some conditions about the columns. Columns must be linearly independent, span Rn, and form a basis for Rn. We did all same thing. We proved same thing holds for rows. Rows are linearly independent, span Rn, and form a basis.